Hello to everybody. Hello, dear friends, and welcome to a new public lecture of Strong 2020 project.
Hello to everybody. Hello, dear friends,
and
welcome to a new public.
I am okay. So I had to mute my YouTube channel. Okay, so here we are at a new lecture. This time we have again two guests with us. This is our sixth public lecture from this series. And let me introduce you what it's about to be today. So today we will have a very, very fascinating lecture about the structure, the 3D structure of the proton. One might wonder how the matter is made of, and we all know that in the nucleus of the atoms there are protons and neutrons. Still today, the structure of the proton and of the neutron are rather mysterious, and we have a lot still to learn about this structure. And our two speakers of today, which I will introduce soon, will tell us where is the edge of the knowledge in this domain. But before doing this, let me tell you some words about our European Strong 2020 project, which I can give you here our channel. So this is the link to our our web page dedicated to the project, which comes from the strong interaction at the frontier of knowledge, and it's financed through the European Union Horizon 2020 Research and Innovation Program. You see here this grant agreement. It's a rather big project which involves 44 participating institutions from 14 European member states. We have also inside one international European interest organization, namely CERN, and beyond that we have one European candidate country and 21 other countries which are participating without benefit from the European funds. So as you see, there are 3,000 researchers involved from 36 countries. And within the project, we have a lot of activities. Part of these activities are devoted to the development of detectors, so instrumentation, which also has an impact for society. Others are devoted to develop the theories which are shaping the hadron physics and our knowledge in this sector. There is still some very interesting funding, these transnational access activities, which means that there is offered access to world-class experimental facilities in Europe, which are COSI, MAMI, Frascati, LNF, ELSA, GSI FAIR, and CERN. And in addition to this, there is also the ACT STAR Center, European Center for Theoretical Physics, which is in Trento. So I think I've convinced you that this is a very important project, European and international. And let me now introduce our two speakers of today. The first speaker, Daria Sokhan, is currently in EIAC in France, where she holds a prestigious grant, namely the Blaise Pascal Chair of International Excellence. Maybe we can make Daria come in. So this chair has been awarded by Île-de-France region. She got her PhD in the University of Edinburgh in 2009. After that, she moved and started a fellowship in INFN for foreign scientists in Pavia. Then moved back again in Orsay in France, while in 2012 she started as lecturer, then senior lecturer at University of Glasgow, which she is presently on leave. Within Strong 2020, she is a co-project leader, co-PI, of one of the work packages which is focused on detector development for next generation facilities regarding the interactions which bring to the knowledge of the proton structure. So Deborah, this gives me the occasion to also greet the people who work from the Department of Dissemination and Education in Frascati, and I kindly ask Deborah to enter Daria so you can see her. So here is Daria, whom I already introduced. Thank you, Daria. The next speaker, the second speaker of today, it's Andrea Signori, who got his PhD in 2016 in Amsterdam at this university, and then worked as a postdoc in the United States at Jefferson Lab and in physics division at Argonne National Laboratory. Presently, he's back to Italy and he holds a prestigious Marie Curie Fellowship at University of Pavia and INFN. He is a theoretician and he works in theoretical and phenomenological studies and development of hadron structure. In particular, I hope he will tell us something about this on the physics of transverse momentum distributions. And they will tell us something today about this three-dimensional structure of the proton. So what it is inside the proton. Having said this, so I know that all of you who are connected are already on our channel, and I also, with publicity to our project, who wants to learn more and to know more, just connect to this website. And with having said this, I invite our two speakers of today to tell us about the fascinating world of the three-dimensional structure of the proton. Thank you for being with us, and thank you all for following us. Thank you.
All right, I guess we can get started. And thank you everyone for being here. Thank you to Catalina for the nice introduction. And thank you also to Daria for agreeing to share the preparation of this lecture today. So today we are gonna talk about the structure of the proton in 3 dimensions. Namely, we are going to try to understand how to describe the physics inside of a proton for neutrons or similar particles in terms of the elementary constituents that we have at our disposals. So I already said a few magic words in this title, but we're going to get clearer later on these concepts. So the outline of this public lecture is the following. In the first part, we're going to introduce some concepts related to protons and what we call here the dynamics of color. So it's gonna be clear later on why we talk color and why we talk about the dynamics of color. Then Daria will tell us something more about the experimental part, namely how you can put a proton under a microscope and investigate the structure of this proton. And then later on in the last part of the talk, we are gonna see some concepts related to imaging of protons, neutrons, and the like, introducing some mathematical concepts which are related to position space and momentum space inside of the protons. So let's get started with the first part, which is about the proton and the dynamics of color. The title of this public lecture talks about the world within. Why do we talk about the world within today? Because the proton is a very interesting object for many reasons, but also because it sits at the boundary between elementary particle physics and macroscopic physics. So in a sense, the physics that we observe in our everyday life, but also for example, in biology or through chemistry, is determined, it's shaped by the properties of the particles like the protons and the neutrons. This is very interesting. But also these particles, like the proton, they are the smallest elementary, the smallest bound state in nature, in the sense that really their constituents are elementary particles. So these are those particles that we don't know how to describe like in greater details. For us, those are the say the elementary objects that we can study. So protons and neutrons together, they account for more than 99% of the mass of the visible world. So this is another very interesting detail about this particle that makes them worth to spend our days studying them. So let's get back to what are, let's say, the forces in nature. So conventionally, we say that we have 4 fundamental forces. Gravity. Gravity is the force that makes us stick to the ground or makes a ball bounce on the ground. So we experience it every day. We also have electromagnetism. For example, it's the interaction that manifests between two electric charges. We have the weak nuclear force, which is responsible for radioactive reactions inside of the atomic nucleus. And also we have the strong nuclear force. The strong nuclear force is actually what keeps protons and neutrons together inside of the core of matter. And it's basically for this reason responsible for the world as we know it today. Without this force, the matter would not be stable, so we would not have also life as we have it today. But the strong nuclear force is also responsible for the structure of these particles in red and in green that you see here. So it's also responsible for the inner structure of the proton and the neutrons themselves. And we're going to see that in greater details later on in this lecture. So let's first of all ask ourselves, what is inside an atom? Which is sort of a weird question, because in principle the word atom means something without parts, but we know nowadays that atoms do contain parts. And the first people who tried to address experimentally this question, in physics at least, are Rutherford, Geiger, and Marsden, who in the 1910s basically devised some experiment in order to test the structure of this atom. So they had diffusion of alpha particles of a gold target, and the result of this experiment, which saw basically beams of these alpha particles scattering all over the place, could be interpreted as if the electric charge in this gold foil that you have here was not distributed evenly in the atoms of gold, but inside of cores, of centers of charge. So that led to the concept of the nucleus. That led to the concept of having an electrically charged nucleus inside of atoms. And basically today we know that matter is almost void, because there is a lot of space actually between the nucleus and the electrons that flip around the nucleus. So the nucleus is built out of protons and neutrons, we know today, but it would be interesting also to ask ourselves if we can repeat a similar experiment at the level of the atomic nucleus. So the question now is the proton elementary, or does it come with a structure? So once we discover the proton and the neutron, did we discover really the elementary structures in nature or not? So how can we do that? So basically at MIT and at SLAC in the United States in the 1960s and 70s, people repeated a similar experiment to what Geiger and Marsden and Rutherford did in the early 20th century. So they had scattering of high-energy electrons off a proton target to explore its inner structure. It's very similar to what the other people did at the beginning of the century, but with a much higher energy scale to test deeper inside the proton itself. So the process is the following. You have an electron here, which is exchanging a photon with the proton target, which is the purple bubble here. And it might be like an obscure figure to look at, but you should keep in mind that this is nothing but a very energetic photograph of the proton. It's so energetic that the photon, which could be identified as the flash of the camera, actually breaks the target, breaks the proton. And from the debris of this reaction, from the remnants, you can reconstruct the structure of your target. So what did people understand? So what they saw is that everything worked. So the result of the experiments were as if the proton was composed by elementary, free, and spin 1/2 particles that were identified with the quarks. So here you have your proton, the big sphere, and the quarks floating around in the proton, the little spheres floating around in the proton are the quarks of the Quark model. So this is what people saw experimentally. Nowadays we know that these quarks actually inside of the proton are not free. They are elementary as far as we understand, but they are spin 1/2 particles, but they are not free. They do interact with the strong interaction, and the source of the strong interaction for quarks and gluons is the so-called color charge. So here you see you have 3 quarks inside of your proton. They can be conventionally named green, red, and blue. and the strong interaction is depicted as the springs that keep these quarks together. So since let's say the intensity of this force is very strong, people named this branch of physics hadron physics, and the particles that are built out of quarks and gluons, they were named hadrons, following the Greek word hadros, which means stout, thick, strong. So a very peculiar property of this interaction is that it confines the quarks and the gluons within hadrons themselves. So no colored particle like a quark or a gluon can be seen, can be measured in a detector, or can be observed outside of an hadron. So that's why the free color charges are red, green, and blue, because if you take the superposition of red, green, and blue, you obtain white, which is conventionally absence of color. So this is one of the key features of the physics of quarks and gluons, and also one of the key features of hadronic physics in general and of the proton. Another interesting feature of the quarks is that they come in 6 families that we again named conventionally up, down, strange, charm, top, bottom. Why we have 6, explaining why we have 6 of these flavors would need like basically another lecture, another public lecture. So maybe we will think about it later on. But what's important to keep in mind is that each family comes with a different mass, electric charge, isospin. Generally speaking, these are things that we call quantum numbers. And these quantum numbers determine the physics, the properties of the hadron that the quarks and the gluon generate. So let's go back to the case of the proton, for example. So a couple of days ago, it was CERN's 67th birthday, and someone decided to celebrate baking a proton cake, which I find very intuitive and useful to show you, because it gives me a hand in order to tell you how a proton looks like in simple words. You basically have the 3 valence quarks, up, up, and down, so 2 up quarks and 1 down quark. And these cookies, the valence quarks, are what determine the quantum number of the proton. And then you have candies and frosties, which are identifiable with the SC of quarks and gluons, namely with those particles, with those quarks and gluons that emerge from the vacuum of the as virtual particles. A proton can be identified with the valence quarks to determine the quantum numbers, but as you see from this simplified picture, there is more to it. There is more than the valence quarks. So, okay, in order to understand a little bit more about the physics of color and the physics of flavor, you should not open a quantum field theory book immediately, but I would invite you to play with this app, which is called Quantum Free, which was developed by our colleagues at Michigan State University in the United States. So this is a very funny and intuitive game in order to understand how to combine flavors and colors together. For example, to build up a proton, you need, we said, 2 up quarks and 1 down quarks. And they have to come also in different colors, because remember, a proton has to be white. It cannot be colored. So you have always to combine together red, green, and blue, for example. So, but I mean, there are, I think, more than 60 levels in the game, so things tend to get pretty complicated, and you can build also pions, you can build delta hadrons, so not only protons and neutrons. You have to combine the quarks according to their spin, so it gets pretty interesting, and I think it gives you like an idea of how the physics works pretty well. So I invite you to play with it, and if you have feedback, please just let us know. So at this point that we know that there are quarks and gluons, we know about the color, we know about the flavor, we know that the color is confined. So what? So can we really understand the structure of matter, the structure of hadron, by working only with quarks and gluons? This is the point. So we need a theory that relies on quarks and gluons that has predictive power. So a theory that we should be able to use both at the analytical level and with computational tools like very powerful computers in order to predict the properties of particles like the protons. You know, in order to predict, for example, the value of the mass of the proton or the spin of the proton or the probability for finding a specific quark inside of the proton. So the theory, we do have a theory. Actually, it's quite complicated. It's quite nice. The theory is called Quantum Chromodynamics, which means the quantum dynamics of color. So this is why the section was named the proton and the dynamics of color. So everything sits into this master formula here. It's the Lagrangian function of the theory. So here we have the quark field, this psi letter here. We have the gluon field, the A letter here. The reason why we say fields is a little complicated, but it's related to the fact that we are not really dealing with particles themselves or cookies. But in principle, using this formula, you can actually calculate, in principle, the properties of particles like the proton. So we should see if we can actually make it or not. So let's start from the global properties. For example, can we explain the mass, the spin, and the size of hadrons working with quark and gluons? Let's see. So the mass of the proton is around 938 MeV. Forget about the unit of measure, MeV. It's something like a kilogram, but it's not actually like it. But let's keep in mind that the number is 938. So we said that the proton contains 3 valence quarks, like 2 up quarks and 1 down quark. So okay, so if we take the mass of the 2 up quarks, the mass of the down quarks, we sum them together, we obtain something like, I don't know, 7, 8 MeV, which is very, very different from the mass of the proton. So you see, if you combine the masses of the valence quarks, you definitely don't get the mass of the proton. So there is already something fishy here, something that we don't understand. Let's have a look at the spin. The spin of the proton is 1/2. It's a fermion. And also quarks are fermions, so they have a spin 1/2. So this is easy. This seems to be easy. So let's take 2 quarks with spin up, like the 2 up quarks. You sum them, you obtain 1/2 plus 1/2. Then you subtract, you put a down quark with the spin down. You subtract 1/2 because it's down. And then you get what? 1/2. So it seems easy, right? You get the spin of the proton. But actually, if you measure the contribution of the quark spin to the total spin of the proton, you observe that the spin of the quark accounts only for 30% of the value of the spin of the proton. So also here, there is something that we don't understand. What about confinement? Confinement is the fundamental property of QCD. So can we explain the fact that quarks and gluons, color particles, are confined inside of hadrons? Actually, no. This is pretty difficult to do, and we don't have a clue how to do it yet. So confinement is very important, but it's also because it's also connected to the formation of hadrons from quarks themselves. So the mechanism that I study nowadays, which is called hydrogenization. Think about it. So an intuitive picture of confinement could be the following. So if you have 2 quarks close to each other and you try to pull them apart, the interaction between these 2 quarks, as you try to separate them, becomes so strong that eventually, instead of separating the quark, you excite virtual particles from the vacuum, as you see from the slide here. You pull the quarks apart, and the energy you put into this separation generates particles from the vacuum. And these particles that are generated from the vacuum, they recombine with themselves, with the other particles, and eventually they form hadrons. So by trying to separate 2 quarks, what you obtain is only creating hadrons, creating colorless particles. So these 2 mechanisms, confinement and hadron formation, are tightly related to each other. But we don't understand precisely in details with the mathematics how they are related and how they work. Institute put together a list of problems which are called the millennium problems that are very important, very deep scientific questions, and that they don't have a solution yet. So confinement, the mathematical explanation of confinement, is one of these problems. And if you actually crack it down, if you write down your solution and the scientific community accepts it, well, you get $1 million. And actually, you get probably $1 million for each of the millennium problems. So if you have some spare time in your day and you want to study physics and try to solve one of these problems, it might be a good investment of your time. no one got it yet. So I mean, it's not as easy, but I invite you to try. So again, there are other things like the internal structure of hadrons, the internal structure of the proton in terms of quark and gluons that we don't understand from first principle working with quark and gluons. So at this point, since we are not even able to understand how these quarks and gluons combine together and generate a proton, it might be natural to ask ourselves, why are we wasting time with this theory? Well, there are at least two very good reasons. The first one is that we want to understand nature, and we know somehow that QCD is the right theory to interpret hadron physics. And the second one is that we still can unlock 99% of the energy that's stored in matter. And this 99% we don't control yet, because we don't really understand how the 99% of the mass is generated. So think about how our society relies on electricity, how much our society benefited from the fact that we can control very precisely photons and electrons, and we can have something like, I don't know, electricity, GPS, and these kind of things. So the implications of controlling at the same level of precision the behavior of quarks and gluons, which are responsible for the 99% of the energy stored in matter, I think would be unimaginable, would be something very interesting to develop in the future. But we are still far from it, but it's definitely worth to try. So now that we know that things don't work and we still want to stick with this theory, we have to say that we know probably where the problem is. So the problem is that sometimes we are not using the right tool for the job that we are trying to do. So here, most of the times working with QCD, what people do is to try to calculate observables, like this letter here, O, I don't know, a cross-section or whatever other observable, as a function of an energy scale, Q. And they do so by summing together different contributions, a leading contribution, which is the first here, the leading in value and in importance, and adding to it perturbations to this value, and which are governed by the value of this alpha letter here, which is the coupling constant of the theory. So alpha tells you how strong the interaction between quarks and gluons is. So what you could do is the following. You could try to sit down and calculate all the quark-gluon interactions that you want to calculate and say, okay, by doing these calculations here, I want to compute something related to protons. For example, I want to compute an observable calculated at the energy of the proton mass, around 1 GeV. This is exactly the problem. So the problem is that the coupling constant of the theory has this kind of behavior as a function of the energy. So when you are sitting at high energy, at high values of Q, these expressions here, these series, these additions, they do produce a numerical value, because alpha is small enough so that you can get at the very end of the calculation a numerical value, a finite numerical value. But if you're exploring something related to hadron structure, so if you're working at low energy, for example, Q around 1 GeV, like the proton mass, then alpha is too big for your expression to converge, to give you a finite numerical value. So this approach here does not have the predictive power, does not work to get physical predictions for observables in hadron physics. We do need alternatives. And these alternatives to this approach can be, let's say, of different nature, but one of the most effective ones is to combine theoretical calculation with experimental measurements. And Daria will tell us more about these experimental measurements and how you can devise and perform them. Actually, how you can put a proton under a microscope.
Sorry, Daria.
the microphone. Thank you.
Apologies, I don't know why I was muted. Thank you. Thank you. Apologies for that. So thanks very much, Andrea, and thank you, Catalina, for the introduction and for just alerting me to this. So I'm going to talk about the experimental aspects of studying the nucleon and of placing the proton under the microscope and how we exactly do this. So, of course, for this, you need essentially a very powerful microscope. So consider how an optical microscope works. Light is an electromagnetic wave. So the smallest objects that we can resolve with it are roughly the size of the corresponding wavelengths that you can see here. And it so happens that the smallest object that we can visually see is roughly the size of a tiny bacterium. Now, to see inside a nucleus and inside a proton, which is, of course, so many times smaller than a bacterium, we need some sort of a wave which has a much smaller wavelength. And for this, we can make use again of the electromagnetic interaction like light, but this time the electromagnetic interaction between charged objects. So this is something that Andrea has already mentioned. So we know that, for example, positive and negative charges attract, but the force of attraction is mediated via a virtual photon, an electromagnetic wave, which we know through quantum mechanics can also be seen as a particle. And this particle we call the virtual photon. Now, the reason we call it virtual is because we can never observe it in its own state. It is only a mediator particle, one that is passed between two interacting objects, for example, a proton and an electron. And this also gives it some special properties. So, for example, its mass does not have to be zero. So to give you an analogy of how we do this kind of imaging of inside the proton, I want to illustrate this with how we would image an object when we look at it from the outside. For example, there's baby mammoth that's been dug out in Siberia. So with visible light, we can see its outside surface. If we want to look inside it, in the structure of the mammoth, we need to go to a form of light or a form of an electromagnetic wave which has a smaller wavelength. And so we could use X-rays, and then we can see the structure of the mammoth inside. And so by analogy of that, this is a little bit like the electromagnetic wave, which is being exchanged between an electron here and a proton with a small wavelength. And when we talk about virtual photons, we don't talk about their wavelengths. Instead, we use a quantity called Q squared, which I will come back to, and which Andrea has already mentioned in a couple of slides ago. And this quantity Q squared is effectively a virtuality of the photon, how virtual it is. The more virtual that photon is, the smaller the features it can resolve. It's a little bit like having a smaller wavelength. So with a smaller wavelength, with a higher Q squared, you can really begin to image inside the proton. And we measure Q squared in units of energy squared. And to give you kind of a reference, and again, you've seen this a couple of slides ago, the energy associated with the rest mass of a proton is approximately 1 GeV. So we want to go to energies above that to be able to look inside the proton. Essentially, to resolve this small structure, you need to go to very high Q squared. So how would we do that? To see something extremely small, it ends up being that we need to build extremely big machines. So we need to get this high values of Q squared in our virtual photon exchange between an electron and a proton. We need to accelerate these electrons to extremely high energies, and then we scatter them from the nucleus of an atom. So in the simplest case, we take a hydrogen atom, and the nucleus of a hydrogen atom is a single proton. So that gives us the ability to look inside the proton. So also for those of you who have studied some physics, Q squared is basically a frame invariant momentum transfer within the scattering. It's how hard the electron hits the proton inside it and the quarks inside it. So our microscopes, we're looking inside the proton and particle accelerators. And here I will illustrate in brief how a particle accelerator works. So you have some tubes, metal tubes, which you can charge either positively or negatively. And you send in electrons, and you use the electromagnetic attraction to accelerate them. So if this initial tube is positive, an electron is attracted to it, it drifts through it, and then as it exits the tube, you flip the polarity. So the tube behind it becomes negative, repelling the electron, and the tube in front becomes positive, attracting it. And so you can accelerate the electron along. But of course, to reach very high energies, you need to build very long accelerators. And so it becomes practical to build them in a circle and build circular accelerators, where you can bend the electrons or your protons, whatever particles you're accelerating, around the ring, and they can also circulate many times, reaching very high energies. So here's an illustration of a number of different accelerators around the globe. There are machines that are not just present in CERN, in Switzerland, where perhaps the world's most famous particle accelerator is, but they're actually scattered all around the world. You can see some in Japan, there are some in China, there's some in the United States, and there are several in Europe. And I will talk in particular about two of these accelerators. So let's start by looking at the one at Jefferson Lab, known as JLab, which is located in Newport News on the coast of Virginia. Virginia is famous for its Navy submarines. It's got beautiful autumn foliage. And of course, it's also famous for its pickup trucks. So this is one of a colleague of mine parked outside of the control room for our experiment. Now, a little bit more details about Jefferson Lab, a bit more practical details about its accelerator. It houses the Continuous Electron Beam Accelerator Facility. It's just known as CBAF. But what it really is two racetrack, two linear accelerators. And then for compactness of space, they're connected into a racetrack. And so the electrons are bent around this racetrack several times, in fact, 5 times typically for its highest energy, and 5.5 times for its highest energy to this experimental hole here called D. The facility has been operating since 1995. It's recently been upgraded to double its maximum energy of operation. And the 3 experimental holes located down here, A, B, and C, receive a maximum of 11.5 GeV energy, and hole D receives 12 GeV. So again, if you think about 1 GeV being roughly the mass of a proton, the energies that these holes are receiving are about 12 times the mass of a proton. So what actually happens inside a scattering experiment? Well, inside this experimental hole, you have an electron beam entering from the accelerator. Then you have a whole bunch of different machines that focus that beam, that monitor its quality and its position. And then the beam impinges onto some kind of target. So the simplest target I've already mentioned is just hydrogen. We use liquid hydrogen compressed into a tiny cell. We keep it at very cold temperatures, basically on temperatures of about 1 Kelvin. And this means that it doesn't, first of all, it gives you a chance to, it compresses it. So you have a dense target. And also, so you want your target, and I will talk about that later as well. And in that case, you also want to keep the temperature of the target extremely cold so that it doesn't depolarize, but just the molecules jostling and losing their polarization. So that, so as I mentioned, hydrogen is just a perfect target for if you want to access the structure of individual protons. And so this electron beam interacts with the protons inside the target, and then some scattering reaction happens and particles fly out. The electron scatters from it. The proton typically recoils somewhere within the detector. And sometimes other particles are also produced in the reaction, and we'll talk about this a bit later. And so, of course, you want to surround your target with different detectors to be able to reconstruct those particles, to track their trajectories, measure their energies, and so work out what actually happened in that scattering experiment. So let's look in a bit more detail about how we actually measure and detect our particles and how we reconstruct the event. So each time an electron scatters, we call that an event. Something happens inside the proton. So actually, the principle of our tracking detectors, something that work out the track of a particle, is very similar to the very earliest detectors we had. So you might have heard or know about bubble chambers, where effectively when a charged particle passes through the material, through the gas in a bubble chamber, it ionizes the material it passes through, and then little bubbles form around their little charged molecules which have been ionized. And so you see visually there's bubbles. Now, of course, we don't take photographs of bubble chambers anymore, but the principle of operation is still very similar. We rely on charged particles ionizing the material they pass through, and then we catch the charges, which are the result of the ionization. They leave little electrical signal, and then these electrical signals can be mapped, and so you can form tracks of the particle pass through a detector. And to make it a more functional detector, we place all of this within the magnetic field and rely on what is known as the Lorentz force. So if a charged particle moves through a magnetic field, it feels a force on it, which curves the particle's track. And depending on the charge, whether it's positive or negative for the particle, it will curve either one way or the other. So here you see a kind of classic photograph from CERN of a bubble chamber, and you see the circles of the particle tracks curling in the magnetic field. The smaller the momentum of the particle, the tighter it curves. Now, another form of a detector is based on the idea of scintillation. So when a charged particle passes through a scintillator material, it emits a flash of light. And then this flash of light can be collected with a photosensor. And so you can measure the total energy that has been deposited as this flash of light. And you can also measure the time of when this flash happened. So this tells you again when the particle hit. So you can build the scintillators into colorimeters and build this around your target to detect the particles. These are not the only types of detectors, but these are two very common ones which are used to reconstruct particles. And so to give you a little bit more details, what do we do with these charged particles? Well, we can look at the momentum from the track curvature in the magnetic field. We can work out the momentum of the particle. Depending on whether it bends one way or the other, we also determine the charge of the particle. And then from when it hit in, for example, the scintillator, we can work out the time that the particle took to fly from the interaction point to the detector. So from this, we can work out its velocity. It's usually represented as a fraction of the velocity of light, c. And we can build up these sort of two-dimensional heat maps of, for example, velocities of all positive particles plotted versus the momentum of these particles. And we see, and because the momentum and velocity are related through the mass of a particle, we see that there are bands in these distributions, and we can associate these bands with specific particles. So here, this band, we can see that here we've identified protons. Up here, we've identified pions, which are mesons. They're very light particles. They move much faster, so their velocity is closer to the velocity of light. In the case of neutral particles, for example, photons or neutrons, they don't ionize, so they do not leave a track. They're also unaffected by magnetic fields. But photons produce signals in a scintillator or a semiconductor detector through what is known as an electromagnetic shower. So for example, a photon, when it enters into the electromagnetic field of the atoms inside a scintillator or inside some material, it can convert into electron pairs, and each one of those pairs can radiate more photons as it travels through the material. And so here you see a representation of this electromagnetic shower. And of course, once you've created electrons and positrons, they're charged, so they leave signals within the scintillator as flashes of light, and so you've detected your photon. Neutrons are very hard to detect. They're a total headache because you have to rely on them knocking into the nuclei. And for example, detectors for neutrons usually are very dense, heavy materials like lead. And then if they knock something positively charged out, well, a proton, out of a nucleus, then this proton is charged, and this can then also leave a signal in the scintillator. So just to show you briefly the anatomy of an experimental hole, for example, this is an image of all of the detectors in Hall B of Jefferson Lab, and it's a huge array of different types of detectors built around magnetic fields, and the detectors that I've already mentioned. So essentially, beam comes in, and then the interaction happens inside, and we use all of these different detectors to reconstruct the particles. Now, the thing about it is that it has a very large acceptance. It covers a very large angular region of space, and so it provides almost full angular coverage. So it's great if you want to measure everything that happened within the scattering interaction. And here's a photograph of the actual experimental hole. The beam would come in along this direction. It's in the stages of construction, so it's an open detector. It's not what it looks like when it's operating. Here you see the electromagnetic colorimeter in the front, and there's a little person on a crane for scale. Now, a different type of detector are the ones that are located in experimental hole C of Jefferson Lab, and there it's a slightly different principle. Instead of surrounding your target completely with detectors, you instead have extremely high precision detectors which you can position in very specific areas of space. And these detectors here, yellow on both sides, they rotate, they're placed on rails, so you can position them in different locations depending on what it is that you want to measure. And this long pipe here is the beam pipe, so the beam comes in along it, and there's a target here in the center. So this means that you can typically measure very high luminosity, make very high luminosity measurements. Luminosity, I will talk about it later again, but it's related to the idea of beam current and target number density. It's basically a measure of how many beam target interactions could possibly happen in unit time. So if you're measuring rare events, you want your experiment, your measurement to have very high luminosity to be able to detect it. And here is those things always look very neat in diagrams, but this is basically what the experimental hole looks like in real life. It is a big mess of detectors. So having kind of looked at how it is that we can measure some aspects of the structure of the nucleon, let's see now how deep it's inside a proton, inside a nucleon you can actually look. Well, this depends on the collision energy. So if you have medium energy, which is what you find at Jefferson Lab, and by medium I mean, for example, center of mass energy of about 2, 3, 4 GeV in these units of energy, then your proton appears to consist of 3 valence quarks. So this is something that Andrea has already introduced you to. And so it appears that each one of these 3 valence quarks carries about 1/3 of the proton's momentum. So that is more or less complete picture of the proton in the valence region. But it turns out that if we dial up the collision energy, the center of mass collision energy, then you no longer see the valence quarks. It no longer looks like it's made up of 3 quarks. Instead, you begin to see a sea of quark gluon, of quarks and gluons. So you have quarks and antiquark pairs popping in and out of existence, out of the vacuum, as you saw in the illustration of hydrogenization that Andrea showed. And you also see that there is a large proportion of gluons, which are the force carriers between quarks. They're the force carriers of the strong interaction. You begin to see them within the proton. And if you go to higher and higher energies, and this is something that has been theorized but has not been observed in experiment, it is expected that you reach a state where you no longer see quarks, you see only gluons. Those gluons completely saturate the entire proton on the inside. And in fact, they are so dense, you reach such a sort of dense, saturated gluon matter that it transitions into a new phase. And we call this phase the color because it's a gluons. Gluons carry color, so these are the force carriers of QCD. So this state has never been observed yet, but this is something that we would like to see, we would like to study, and we'd like to be able to measure. Now, to reach these kind of energies and to reach this regime of imaging the proton in this detail and in this resolution, we need to build a new machine to be able to do that. And this is something that's called the Electron Ion Collider, and this is currently in development. Again, at a site in the United States on the East Coast, in Brookhaven National Lab. So the construction will begin soon, and the start of experiments should be in about 10 years from now. Now, just to give you the kind of main points of the Electron Ion Collider. So I've talked about measuring studying the proton by colliding electrons with a stationary target. But you can't get very high center of mass energies like this, or at least you could, but it's very expensive on the electricity. So a more efficient way of achieving high collision energies is to use a collider. So use 2 accelerators, accelerated beams of electrons and beams of protons, or even ions, nuclei, that you collide with each other. And so this is what the electron ion collider will do. And it's going to have polarized beams of electrons, protons, deuterons, helium, so light ions, and it will also collide electrons with unpolarized heavy ions all the way up to uranium. So it will have a very big range of center of mass energies, up to about 140 GeV. We expect that this should be enough to be able to see this saturated region of gluons. And it will operate at a very high luminosity for a collider. So this is really pushing the technology that we have for accelerators and for detectors at the moment right to the limits. And we're also working on new technology for this. So the tagline for this collider is that it's really going to study the glue that binds us all. So EIAC community is extremely large. It's got about 1,300 scientists from more than 260 institutions from 35 countries scattered all around the world on all of the inhabited continents. And at the moment, we have a lot of accelerator scientists and engineers who are designing the beams, the interaction points, the crossing points for the beams, and all of the associated infrastructure. Here you see a photograph of a colleague working at Brookhaven National Lab on the beam line. And we also have a huge community of nuclear, hadron, and particle physicists and engineers who are defining exactly the physics that the EIAC will be able to do and what requirements this places on the detectors and designing the detectors. And in fact, this is something that we're doing with funding from the Strong 2020 as part of the Strong 2020 grant, as Catalina mentioned at the beginning. So at this point, I will pass back over to Andrea, who's going to talk about the kind of imaging that we can do with these machines.
So now that we know a little bit more about accelerators and detectors and how you can put a proton under the microscope, let's see what we can do when actually we have the proton in the microscope. So the idea, as we said in the very beginning, is to have some kind of imaging of the proton. So what is imaging? With imaging, we mean extracting images of these of particles like the proton, the hadrons in general, from experimental data. So it follows more or less this strategy. So you get experimental data from people like Daria who work on the experiments. They measure quantities like cross-section, so the probability of interactions, or differences or ratios of these cross-sections. And we have to try to get these images from the data. So how does it work? So, well, one takes the theory, QCD, Quantum Chromodynamics. It combines it with computing resources, so programming languages and computing resources like very powerful computers, not like the ones that we use every day. And we build programs that are able to extract these images from the experimental data. So the image that you see here is actually from a recent analysis of proton structure of experimental data. And it's informative about proton structure because it tells you what's the probability of extracting a specific quark from the proton, or observing that specific quark of a specific flavor within the proton as a function of the velocity of the quark itself. So you see that you have these contour plots that tell you how the probability changes with the momentum or the velocity of the quark itself. So which kind of distributions or maps of hadron structure can we define? So there are several maps that you can define from the theory point of view, at least. The ones that we are going to address today, they come all from the so-called Wigner distributions. These are very generic maps that you can analyze to get information about, let's say, the probability of finding a specific quark, like the blue bubble here inside of the proton here, in position and in momentum space. So, for example, the Wigner distribution will tell you information on the position, the transverse position, the variable bt here, the velocity xp of the quark, the velocity which is collinear to the direction of motion of your proton, and the transverse velocity of the quark with respect to this direction of motion. So unfortunately, these very generic maps, the Wigner distributions, cannot be easily studied combining theory and experimental data. But what one can do is to have projections of these maps that are actually pretty easy to match to experimental data. For example, if you remove the information on the position BT, you can define objects which are informative on the collinear and the transverse velocity of the quark. So the so-called transverse momentum distributions, TMDs. If you also remove the information of that on the transverse velocity of the quark, you get distributions maps that tell you what's the probability, for example, that your blue quark inside of the proton has a specific velocity or momentum. These are the collinear parton distribution functions, PDFs. One can actually do something different, namely you can neglect or integrate out the information on the transverse momentum, and you get maps which are sensitive to the collinear velocity and the transverse position. And Daria will tell us more about this later on. So these are related to the so-called generalized parton distributions, GPDs. And furthermore, if you integrate out the collinear velocity of the quark, you get objects which are related to the so-called form factors, so objects that are informative only on the transverse position of the quark with respect inside of your proton. So you see, it's like we are observing an object from many different perspectives. You cannot grasp information, you cannot get information about the proton as a whole, but we can only access different, we can only see a specific slice or projection of the objects. It's like the tale of the blind man and the elephant. So you see, elephants are interesting animals if you want to talk about high energy physics. Daria already had 2 pictures, and I think this one is as useful as well. So this blind man, they try to understand how an elephant looks like, but they, of course, they are blind, so they have to touch it in from different angles, and everyone gets a different information, and it looks like something which is not the global information. So good physicists are usually also good philosophers, and we know that in science, as in life, we obtain global knowledge only combining different perspectives. So this is actually what we do also in nuclear physics when we study the proton. So in specific, related to the maps in momentum space, what you can do is to try to observe your proton with a probe like the photon that also Daria explained before, and you can be sensitive to the motion of these quarks or also the gluons inside of the proton as a function of the longitudinal momentum, the arrow here, the momentum which is longitudinal with respect to the big arrow, which represents the direction of motion of the proton, or the transverse momentum, which is the smaller arrow in the plane. So if you want to study the physics of your quarks only along this direction of motions, you can use the so-called collinear parton distribution functions, which are the functions f1 of x, and x is this variable here. So they give you information on the structure of quarks in momentum space in 1 dimension. Instead, if you add the transverse momentum dependence, you can get a picture of the quarks in a 3-dimensional momentum space. So that's why we talk about the structure of the proton in 3 dimensions. So these functions are richer than the previous one, but they are also more complicated to study. So one of the ways we actually get experimental data which are informative on transverse momentum distributions is a process called semi-inclusive Dipolastic scattering, where you have a lepton that scatters off a proton target, and you measure a lepton in the final state and another hadron. So this process here has been measured by the Hermes collaboration at DESY in Germany, COMPASS collaboration at CERN, by collaborations at Jefferson Lab, and it will also be studied at the future Electron Ion Collider. So how does it work? We know how to calculate the cross-section. The cross-section is usually a combination of something which represents the hard interaction H between the quarks and gluons, and something which is related to hadron structure. So the convolution of these functions here, the transverse momentum dependent distributions and the transverse momentum dependent fragmentation functions, which are the functions that tells you, for example, how a quark neutralizes the color and transforms itself into a pion before entering the detector. And the experimentalists give us the data for the cross-section. So they give us a number for this quantity. We know how to calculate H. the hard interaction between quarks and gluons, and the rest we extracted from the experimental data. So the yellow box here represents actually the maps that I was presenting before. So it's kind of an inverse problem, right? So we get measurements for a quantity, but we know how to calculate another, and we extract the maps basically by inverting the problem. So this is important because it tells us that we have to have different experiments in order to get different pictures of the proton structure. Different experiments come with different kinematic reaches. For example, Jefferson Lab experiments are more focused to the lower energy part, whereas COMPASS and the Electron Ion Collider will explore higher energies. And according to the energy of your experiment, you will actually get a different handle on proton structure. At lower energy, as Daria said, you will see the valence quark, whereas if you increase the energy, you will see more and more the C quarks, the particles that are popping out of the vacuum, and the gluons themselves. So these are actually examples of the maps that you can extract from data. So you see at the end of the seminar, you see actually these maps. This represents the current knowledge that we have for the maps of hadron structure in momentum space, at least. So these are the one-dimensional distributions. They tell you, for example, what's the probability of finding here the blue band. It's the probability of finding an up quark in the valence sector, so one of the free quarks for the proton, for example, with a specific velocity, and also the same for the other bands. But also you can get pictures for the transverse momentum distribution. So this is what we get usually after 1 or 2 years of work. They seem simple pictures, but there is really a lot of work behind these pictures, and they have several implications. You can also have two-dimensional pictures if you project out some information. And for example, this kind of traffic light picture here tells you that the distribution in momentum space for different flavors is actually different, which is something important to keep into account when you study high-energy physics experiments. So I think at this point, I can give the ball back to Daria, and she's going to tell you a few things about the position space distributions, right?
Let me unmute this time. Thanks very much, Andrea. Okay, so transverse position imaging. This is something that we could also do, but using a different type of process. So the thing that a little bit like you've just heard about transverse TMDs, transverse momentum distributions, another form of another type of function that we can use to describe the internal structure inside the proton, which is something that Andrea has already mentioned, is called generalized pattern distributions. I'm going to call them GPDs for short. And we can interpret these functions as relating the transverse position of the quarks and gluons, the partons inside the nucleon, to their longitudinal momentum fraction. Now, this comes from the experimental perspective, because what is transverse and what is longitudinal, you need to pick an axis. So in this sense, we're picking the axis of momentum transfer. It's basically this virtual photon which is exchanged in the scattering that defines our axis, and then we can map out the distribution transverse to that axis and connected to the momentum carried by the quark along the longitudinal direction, so along that axis. And so this basically gives us the ability to form demographic images of the nucleon. So effectively, we can do scans of position of the quarks or gluons at different momentum fractions. And in fact, this is a picture that you've also just seen in Andrea's part of the slides, where depending on what our energies, our collision energies are, depending on what our Q squared is, the momentum transfer in the scattering, we look at either the valence quark region, or for example, we look deeper into the nucleon, into the proton, and we can see the quark, anti-quark pair distributions, or even the distributions of glue. In transverse momentums and transverse position space. I'm sorry. So what is the process that actually gives us this information? So of course, when we scatter an electron from a nucleon, there are loads of different processes that take place. And different processes will give us different information. So you've already heard a little bit about how we can access transverse momentum distributions. So to access GPDs, we need to look at a process that is known as deeply virtual Compton scattering. And so before I talk in proper detail about it, I just want to give you a cartoon of what this actually looks like from an experimentalist perspective. So before the scattering happens, you have an electron that crashes into a nucleon, a proton, say. Let's say that you've got them colliding as two beams. After the scattering, this is down here, the electron has scattered somewhere. The proton or the nucleon has recoiled. Effectively, it's also scattered into some other part of space. And you have emitted a very high energy photon. And that very high energy photon comes from deep inside the nucleon. It's basically been emitted by a quark that you have hit during your scattering. So a diagram that we use as physicists to look in more detail at this process is here on the right. It's exactly the same process. I will explain what is shown here. We've got an electron beam that comes in, it scatters. As I've mentioned before, the scattering process is the exchange of this virtual photon. But if you hit your proton with sufficient momentum transfer, i.e. your q squared is sufficiently large, then that virtual photon doesn't just scatter from the proton, from the whole proton, it scatters, it hits, it pings off an individual quark. And so you transfer a lot of momentum in that scattering, you transfer that momentum through this virtual photon, you hit a single quark with that photon, and this is represented here as this red line. You're hitting that quark, that momentum has to go somewhere. You don't break up the proton stays intact. So the quark remains within the proton. And so this momentum has to go somewhere, and it goes into the production of a real photon, very high energy real photon, which is emitted within the scattering. And so to be able to measure this, this process and also obtain information on GPDs, you need to detect the scattered electron. If you just detect this, all you're probing is longitudinal momentum carried by the quark. But if you also want to know where that quark was positioned within the proton, you also then need to detect the emitted photon and also catch and detect the recoiling nucleon. So you need to measure all of these three final state particles. And we call this an exclusive reconstruction of the event because you've excluded every other form of interaction process that could take part, that could also be a part of scattering, but it would be a different process. So we call this deeply virtual Compton scattering. You might know Compton scattering, which is basically just a scattering of a photon where the photon itself recoils, but because you're using a virtual photon to do the scattering, we call it deeply virtual. And it's deep because it's deep from inside the nucleon. Now, this isn't the only access to GPDs. There are other related processes. For example, your final state photon that you've produced, your high energy photon emitted by the quark that you have hit extremely hard, that could be also a virtual photon instead of a real one. And if it's virtual, it will decay into electron-positron pair. And that process is called double DVCS. It's extremely hard to measure experimentally. But there are other related processes. For example, time-like Compton scattering. It's like DVCS. Well, it's a bit like double DVCS. Your final produced photon is virtual, but your initial photon that comes in is not virtual, it's a real one. I'm not going to go into details about how we could produce these real photons for the scattering experiments, but these experiments are also happening at Jefferson Lab, will be happening at the Electron Ion Collider. Or, for example, instead of producing a high energy photon, you could have a process that is like DVCS, deeply virtual Compton scattering, but instead of the high energy photon, you could produce a meson, a quark-antiquark pair. And all of these provide complementary information on GPDs. You cannot get full information on GPDs from measuring just a single process. You need to measure different processes under different conditions. You need to pick different collision energies to look at different scales, at different resolutions within the proton. You want to measure them at different q squared, a different momentum transfer, different photon virtuality in that scattering. You sometimes also want to look at different electron and nucleon polarizations. And so you take data from all of these different experiments, and then you can analyze it together, and this gives you information on GPDs within a kind of global fit to all of these data. So a very brief slide on how we can access GPDs actually from these measurements. Andrea mentioned already cross-sections. So cross-sections, they're related to probability distributions for a particular process under particular conditions. In practice, this means we just count numbers of events for particles that have been produced in a particular process, for example, deeply virtual Compton scattering, and that have been scattered with certain momenta into certain regions of space. But then this sounds very easy. We sit there and we count particles. Well, we don't, but computers do. connected to the detectors. But actually, to extract these cross sections is a very complicated process. You need to know your detector effects very, very well. There are a lot of background processes that are happening at the same time and that you need to be able to subtract. So this is a process that really takes years. It takes years to take the data with their measurements, but it also takes years to analyze it. And so what do these cross sections look like? Well, here's an example of one. This is a measurement of the cross-section plotted versus an angle, characteristic angle for this deeply virtual Compton scattering interaction. So we find these sort of distributions, angular distributions of cross-sections. We can also measure asymmetries. Asymmetries it's a case where you, for example, pick a particular electron polarization, you'd make a measurement, and then you flip the polarization of the electron and you make exactly the same measurement. And then you build what is known as an asymmetry. You take the difference between the numbers of these events over the sum of the numbers of the events from those two types of measurements. And so here, for example, you see an asymmetry which was produced by one of my students for this deeply virtual Compton scattering process. And you might recognize it as looking like a very nice sine wave. So in fact, this is a very handy way of accessing information related to GPDs, because it turns out that if we look at these asymmetries, also cross-sections, but cross-sections are a bit harder. You need to consider a lot of extra effects for them. But if you look at the asymmetries, a lot of the extra kind of detector effects, for example, just cancel out because they're both on the numerator and in the denominator. And we see that actually this asymmetry is parameterized, so it's plotted again as a function of phi of this kind of angle in the interaction, and it's parameterized by functions related to GPDs. And so you extract the amplitude of this sine term, and this tells you something about GPDs. So this is as much detail as I'm going to go into. But this is effectively how we obtain this information experimentally. And what this gives us is that once we've obtained generalized pattern distributions, as much information as we can about them from different measurements, different processes, from different experiments around the world, we can begin to build up these tomographic pictures of the nucleon. So for example, here on the left, you see the transverse distributions of up quarks inside the nucleon plotted versus different momentum fraction x that they carry. And so we see that it appears that when the momentum fraction x is around a third, so we're looking at the valence quarks, then they're collected a bit closer to the center of the nucleon than when the momentum fractions are very low. So this is where we're looking really into the quark gluon C. And so it looks like the quark gluon C is spread further around to the periphery. And so these are really, at the moment, more or less artist impressions of what a proton looks like, because we do not have enough data yet to be able to constrain this full range in X and to be able to do this accurately. But we begin to see kind of hints of these properties of the proton. And here you see a kind of different representation, which was done with a different analysis, a kind of global analysis of all available data. But again, on the y-axis, you see the kind of spread of the up quarks plotted against the fraction, momentum fraction that they carry. And we can also look at residual polarization of the up quarks, for example, again, as a function of X. So we get a kind of tomography of the polarization inside a nucleon. And other things that we can extract from GPDs is that they also carry information about pressure distribution. So again, this is a plot here on the right. You can see pressure distribution plotted as a function versus the radius of the nucleon. So we see that we expect the pressure to be large and positive, maybe further towards the center, and then negative as you go out towards the periphery. And of course, overall, the pressure has to be zero because the proton does not explode or implode. And we do not have enough data at the moment, but these are the kind of images that we're beginning to build up, and they will get more precise as we obtain more data. So she said that these images are built really combining model assumptions and measurements together. They don't show the uncertainties that we have on the measurements or on the model assumptions, but they're an indication of what we're able to do by accessing these generalized pattern distributions, what kind of tomography we can do with this. And the next decades will be really crucial in deepening our understanding of the structure inside nucleons. So this is my last slide. I will pass over back to Andrea for a summary, and thank you very much for listening to us.
Yes, thank you, Daria. So the summary is a piece of cake now. So we just have here our proton, and we want to close the seminar by reminding you that combining experimental information with theory methods, what we can get are maps of proton structure, both in momentum space and in position space. These maps, as Daria just said, I think it's a very important thing to remind ourselves and also the people who are not directly involved with the calculations and the measurements. These maps are partial results. In a sense, there are uncertainties both on the measurements and on the theory calculations, but we are doing our best to get precise information and to do something which is as close as possible to reality. So here on the left part of the screen, you see the momentum distributions, whereas on the right-hand part of the slide, you see what Daria presented us so far, which is related to GPDs and the information for the quark and gluon structure in position space. So I hope you enjoyed the seminar, and if you have any questions, please feel free to reach out to us. Thank you.
Thank you very much. Thank you very much, Daria and Andrea, for this fascinating presentation of which are our instruments, both from theoretical side and experimental side, to understand something which in principle might look simple, the structure of the proton. And you have shown to our listener and to those who will see the seminar, which stays online, how actually fascinating and complicated these type of studies are. So there is a lot of work still to be done to understand even something which looks pretty simple, at least from outside. And I see as well there are people who are thanking to you for this interesting seminar you have prepared. Now I want to ask those who are listening to us, I know that there are also colleagues, so not only public, general public, but there are also some colleagues. If you have some questions, please write them down here in the chat, and we can ask our two speakers of today who are working in this field. And as Daria has shown, actually there is an all research, also from experimental point of view, pointing to the next 10 years with this electron ion collider. So I see a question from Susanna Coito. She asked, is it possible that at high energies, some fraction of the C quarks actually converts into new constituent quarks? Could we distinguish such new valence quarks in the experiment? So I don't know if any of you wants to.
Okay, I think, well, I will have a go with this. So it is true that the C quarks, I think there is nothing really that tags a quark and says this is a valence quark by itself. What makes it a valence quark is that it's a quark that carries a third of the momentum of the nucleon, roughly. So if during your scattering you have perturbed the quark somehow, you have done something to the quark and you've given it a bit more momentum, then yes, it can become a valence quark. But essentially, if you take the quarks by themselves, they're indistinguishable. Basically, this kind of idea of what is a C quark, what is a valence quark, it depends on the momentum fraction that it is carrying. And then if you take a C quark and it becomes a valence quark, then some other quark has become a C quark to keep this balance of quark-antiquark pairs that pop in and out of existence from the gluon.
Yeah, thank you, Daria. That's true. I mean, if I may add, the concept of valence versus C quarks is in a sense artificial. I mean, of course I was oversimplifying the discussion when I showed you the cookies as the valence quarks or and the candies as popping out of the vacuum. So the more accurate picture that we can have in mind is that the proton is like inside of the proton you have a whole sea of particles popping out of the vacuum, and what we call valence quarks is on average the difference, for example, between up and anti-up quarks. So in a proton, on average, you have the difference between the quarks up and the anti-up quarks is 2. And that tells you that you have 2 valence quarks. And something similar for down quarks. And these relations are different from hadron to hadron.
Thank you very much, both to you, Daria and Andrea. So your last chance to ask questions. Yeah, I don't see other questions popping up. So then allow me to wish you a lot of success in your work, which it's bringing us farther and farther in understanding these issues, which are really important for understanding what we are also made of, since we are made of protons and neutrons. And we see how complicated it is when you are looking carefully with all the instruments, the science and principle, the modern physics is providing. It's really fascinating, and I wish you a lot of luck in the near future to unveil more and more by using theoretical instruments combined with the experimental research, also with the instruments developed within STRONG 2020, this structure, the 3-dimensional structure of the proton. And with this, I thank to all those who are following us in today's lecture. Stay in touch, stay tuned, follow us on our webpage. We are now working to prepare the next lecture. If you have suggestions, also contact us to put your suggestions forward. And once again, thank you, Daria, and thank you, Andrea. And moreover, thank to all the staff from Frascati, whom you do not see because it's behind the scene. So there is an all staff of educational and dissemination. In particular, today we are joined by Deborah Bifaretti and by Sara Arnone, who are just working behind the scene. And thank you very much also to all the staff of Frascati who allows us to have these beautiful seminars like the one of today. Thank you, and bye-bye to everybody.
Goodbye, thank you.
Bye-bye.